All right, what's up, guys? I'm just going to work out this one problem for you from last week's quiz because I didn't have time in recitation, and I think it's like a good problem. Hopefully, after watching this video, everybody kind of understands what needed to be done here. So, we're not really given a whole lot in the problem statement, right? So, really the only thing to declare is just that this angle is 75.5 degrees, I guess. Okay. That's the only number that we have. Okay, so for problems like this, one of the first things you want to do is you want to make probably a very large, clear free body diagram. And by the way, I apologize for like the black bars on this recording, but I have like a monitor with a very weird resolution, and I couldn't really figure out how to make it take up the whole screen, so hopefully that's not too distracting. Anyway, let's get a free body diagram made up, right? So this is kind of what you want to do, right? So let's talk about this. We have I just kind of realized that I should have specified some things. There is so what I just noticed, right, is that I didn't specify that the angle here, that this ladder, right, the ladder is the black, the black line. The angle that it makes with the horizontal is going to be this theta, the 75.5 degrees. So if you're going to, as you're watching the video, go through and reconstruct, the work that I'm doing here, you probably want to specify that this angle here, right, the ladder, or the angle that the ladder makes with the horizontal is theta, okay? And we'll, be using that fact as we go through and solve. But other than that, I think this is a fine diagram, and it has everything that we need, right? So, let's just start summing some forces here. Okay, so remember that for static equilibrium, we want to add up all the forces in the x direction and set their sum equal to 0. We want to add up all the forces in the y direction, set their sum equal to 0, and then also compute the torque, right, about some axis of rotation, and also make sure that that is 0 as well. Okay, so let's do this. The net force in the x direction, I'm going to change the size of this font just to make it a little bit bigger. I don't know how helpful this will be, but let's see. So the net force in the x direction, okay, is just going to be the static friction force here, right? That kind of prevents the ladder from sliding out, and the normal force up here. Now, if you're not sure which direction the static friction force should point, maybe an easy way to see that is that we just demand that all the forces in the x direction, cancel out, right? So if I had made my static friction force pointing to the left, say that I would look at that and know that it couldn't work, right? Because the static friction force is then pointing in the same direction as this normal force, right? This is the force that the ladder experiences because it's in contact with the wall. And then, I wouldn't have static equilibrium, okay? So I'm going to write this. I'm going to write Fs minus N2. Is that what I called this one? Yep. N2 is equal to 0. And that's it for the x equation, right? And so that's one of the nice things about static equilibrium, is that your x and y equations are usually pretty easy and nice looking. And so let's also do the y direction. Okay, so here I'm going to have to account for the normal force that the ladder experiences, right? And this is being exerted on the ladder by the floor. And then from that, I'm going to have to subtract both of these gravitational forces, okay? So I have the normal force 1 pointing up minus big up. It's hard to type when I can't see my keyboard because of the microphone, but normal force 1 up, and then both the gravitational forces down. Okay, so big M, right, is going to be the gravitational, or sorry, big M is going to be the mass of the ladder, and little m is going to be the mass of the person. And we'll talk more about where exactly we want to put the person in this particular situation, in a bit. But for now, if we're just thinking about the y equation, it doesn't matter all that much because you know, we know that the gravitational force has to act straight downward, okay? So one other thing to notice about the free body diagram here is that the mass of the ladder, right, is sort of, or the gravitational force of the ladder is sort of being placed at the ladder's center of mass. So if the ladder is, you know, L meters long, then this is at a position L/2 from the axis of rotation, which is going to be down here, okay? But we'll definitely get more into that when we talk about the torque. Okay, so far so good, hopefully. What I probably want to do is maybe just rewrite my x equation here. And what I'm going to do is I'm going to say that the static friction force has a magnitude, right, that's given by mu sub s n1. And so it's important to point out that this is the maximum static friction force here, right? Because remember that static friction is defined via an inequality. And so, you know, it could be this value that I've just put down, which is the coefficient times the normal force, or it could be, you know, anything less than that. But all we can really do most of the time is just say that we're going to solve for the case where the static friction force is at a maximum, and then, you know, once we get our answer, we can kind of deconstruct the results and see, you know, maybe what would happen if the static friction force were not at a maximum, if we need to do that kind of thing, okay? So rewrote this, right? So now I have that some coefficient times the first normal force minus the second normal force equals 0, okay? So we're going to just leave this equation here for a second. We'll come back to it because now I'm going to go back to the y equation, and I'm going to write that n1 is equal to big mg plus little mg. Okay, so now I can plug that into this equation. And I can say that mu s times big mg plus little mg minus n2 is equal to 0. And I think that's all we can really do here with the x and y equations for now. We'll come back to them in a little bit. But I think that now we kind of have to consider the torque, right? So the net torque, and I'll just put like a z in the subscript here. So that sort of suggests, right, that my z-axis is pointing into the screen, right? Because, or sorry, out of the screen, right? Because x cross y is z, so z should be, positive z should be pointing out of the screen, right? So positive z comes out of the screen, negative z goes into the screen. Now, when computing the torque, right, I've put my axis of rotation here at the origin, right, where x and y are both 0. So I don't have to consider n1 or the static friction force when I'm going to write my net torque out, right? Because they are 0 distance away from the axis of rotation, meaning that they don't contribute to the torque, right? So what my equation is going to look like for the net torque then, and I'm going to have to probably go back and forth here because I'm really zoomed in because I want to make sure this is large enough for everybody to see. But it means that I can't look at, you know, everything all at once, right? So let's just talk about this for a second before we start writing things down. Now, both the gravitational forces will tend to make this thing rotate clockwise, right? Because I don't know, you could like hold your pencil up or something and pull down on it in this kind of way to convince yourself that that's, you know, what's going to happen if you can't see that, right? But you know, maybe you can just look at it and see, and that's good. So then the normal force, right, n2 is going to tend to make this thing rotate counterclockwise. So n2 is going to have a positive torque associated with it, and both the gravitational forces will have negative torques associated with them, okay? Now, let's start filling this torque equation in. I'm going to write negative big M G L/2, right, where I'm saying big L is the length of the ladder. And this is not quite complete, right, for the torque due to the ladder's gravitational force, because this is like saying that all of the gravitational force contributes to the torque, when in reality it's just going to be the component of the gravitational force that's perpendicular to the ladder, right? So kind of like, if you can see my cursor, I think you can, yeah. This line that I'm sort of drawing right here, right? This would be the perpendicular component of the ladder's gravitational force. Okay, so we have to figure out what that is, and what is that? That's going to be cosine theta. Yes, cosine theta. Okay, so negative big mg L over 2 times cosine of theta. Yeah, and so it's weird that it's not sine, but you know, the cosine of the let's say the exterior angle here is the same as the sine of the interior angle here. Is that true? Yes, it's true. It is true. Okay. Yeah, you should put this in on your sketch just to confirm this, right? But I'm confident that what I've written is correct. Right, because the non-parallel component of the gravitational force will not contribute to the torque. Okay. So there's that, and then we have to account for the gravitational force of the person. Now we've sort of in our diagram just put the person at some arbitrary length up the ladder, right? And what I'm going to do next is maybe going to be a little bit confusing, but you know, it's a good thing to see somebody do at some point or another, you know, to sort of reinforce how the math and the physics must you know, correspond, right? So what I'm going to do here is I'm going to say that first of all, the magnitude of the gravitational force is obviously mg. And then I'm going to say that this person is some arbitrary length up the ladder, and I'm just going to introduce a constant beta, right? And then I have to remember that I should tack on a cosine of theta here. Now, let's say if beta is greater than or equal to 0 and less than or equal to 1, right, this allows for me to kind of just plug in any value for the moment arm of the person on the ladder, right? Because in the case where beta is 0, that means the person is essentially standing at the very bottom of the ladder, right? They're pretty much standing at the axis of rotation. And if beta is 1, that means they're all the way up to the top of the ladder, okay? And this might be something you might do because maybe you don't know, or you can't immediately see what the condition is for the maximum torque exerted by the person, okay? And if I'm not thinking too hard about this, like I can't see it, okay? So this is something that like I might do when solving this problem. But if you can see that you know, the maximum torque should just be when the person is all the way at the top of the ladder, that's fine too. And I mean, it sort of makes intuitive sense that's, you know, the real life condition where the ladder is most likely to start slipping, okay? But maybe you don't know that if you've never been up a ladder, right? Anyway, so there's that. And then the last thing to do is to account for the torque of the normal force right here, right? And then I'm just going to try to do this in my head, but if we want the component of the normal force that is perpendicular to the ladder, it looks like that is going to be hang on here, I'm struggling a little bit. So the normal force looks like this. Maybe I'll just draw this so you guys can see what that looks like. Bear with me here. I mean, this is also for me. So how do I? Yeah. Okay, this is fine. So I'm just gonna put this into Paint real quick, and then I'm gonna make a very awful sketch. So what I want to do is I want to draw the normal force probably acting at the point, like this. Okay, that's supposed to be a straight line. And I'm writing with my mouse here, so don't judge me. Okay, N2. And then I'll just go ahead and get rid of this other one for clarity's sake. So let's just delete this. Okay, well, it's checkered. That's funny. Okay, I guess this is transparent. So then what I have, right, is I have the perpendicular component of the normal force that looks like this. I might call it N sub perpendicular. Okay, and then I have the parallel component, which looks like that. That's really bad, but hopefully everybody can see what I'm trying to draw here. And parallel, is that big enough? I think it's big enough. Okay, so if this angle right here is theta, okay, then that means this angle right here is also theta, right? Because these are the interior angles of a line that passes through two parallel lines, that intersects two parallel lines, right? So then I can see that the perpendicular component of the normal force actually corresponds to sine theta in this case, right? Because the perpendicular component of the normal force here could be written like, or could be drawn maybe like this. Okay, so that's going to be N2 sine theta. Yes, sine theta. Okay, I've convinced myself. Hopefully I've convinced you too. So then plus N2 L sine theta. Okay. And this we want to be equal to 0, right? We want to demand that this is equal to 0. Yeah, so that's cool. Now, we can go through and we can simplify this equation a little bit, right? We can go through and we can cancel every L that we see, right? Because those are common to every term in the equation. So we might as well just do that right now. So I'm just going to write negative 1/2 mg cosine theta, right? Minus, we'll put the beta in front, beta little mg cosine theta. Plus N2 sine theta. This is still equal to 0, right? Because it's kind of like we're just dividing both sides by big L, right? That looks good, I think. Yeah, I want to make sure that I'm not like losing any terms here, right? Because as you go through and you write these toric equations, there's going to be a lot of different variables floating around, so you have to be careful, right? So then what I can do here is I can come back to my x equation, and I can finally use this to write that the normal force, the second normal force, is just going to be the coefficient of static friction times the sum of the masses, g, right? That's good. And then I can just like rewrite this equation one more time. I might even, you know, write it again, but I'm just going to take this, right, this mu sub s m plus m g, and I am going to plug it in for n2. So now we have this, right, and we can cancel the g's as well now, so that's cool. Right, we can go ahead and cancel those out. So this is my equation. Is the problem asking us to do it again? What minimum static friction coefficient between the ladder and ground did the manufacturer plan for? So we have to solve this for the static friction coefficient, right? And how? I mean, I can do that in Mathematica pretty easily, but it's like, you know, it's kind of some gross algebra. I feel like there's something I'm missing maybe that's going to simplify this a bit more, but let's just try this, see what Mathematica has to say. Right, and it's not that I couldn't solve this by hand, it's just that, you know, I have this resource right now and I'm gonna use it. And maybe this is good, this is a good demonstration of Mathematica's capability. So what I'm gonna do is I'm gonna put my equation in, right, say solve. I've copied the equation out, I'm gonna set this equal to 0. And then I tell it to solve for mu. I typically avoid writing subscripts when I put things into Mathematica just because sometimes it does weird things, especially if you use like numerical subscripts. But I think that hopefully what I've written here is clear to everybody. So let's see what it gives us. Okay, it gives us this gross expression. But you should remember, right, that that cosine of theta and cosecant of theta here are just numbers that you can evaluate, right? Just numbers that you can evaluate. And so I'm going to make Mathematica simplify this. And it works out to be a little bit nicer, okay, right? So somehow... Oh, I see it, yeah. So cosecant of theta is like 1 over sine theta, right? So it is able to just basically put that all in terms of cotangent of theta. So what we find is, just gonna drag this over here, is that this coefficient, not u, mu sub s is equal to big M plus 2 beta M cotangent of theta. I can mostly touch type, actually. It's just kind of sometimes when I'm recording and my attention is a bit divided, it's a little harder, so bear with me on that. Now, cotangent of theta is just a number, right? Beta is just a number. I mean, everything here is just a number. None of these things are actually variables. Oh, so we're supposed to assume that a typical user has twice the mass of the ladder. That's what I'm missing. Okay, so this is fine. We can just go back to Mathematica, and this is why Mathematica is great, right? Because I can just say, all right, Mathematica, now tell me what this looks like if the mass of the ladder is double the mass of the person. And that's what it was, right? It was double the mass of the person. No, other way around, sorry. Okay, so the mass of the person is double that of the ladder. So let me just fix that. It doesn't really matter though, right? Because, but if I want to be consistent with my notation, I'm going to say that little m is double big M, okay? Then we get this, and then I'll have it simplify this, even though probably everybody can see that the masses will cancel out. And then we get this nice result, which is that this is, I'll write it exactly as Mathematica wrote it, 1/6 plus 4 times beta times the cotangent of theta. And this is just a number, right? Well, I mean, beta, again, we could say it varies between 0 and 1, but, you know, it's just a number. It's just a pure number. And this is a sensible result in the sense that it doesn't have dimensions, right? So I'm always telling you guys to think about units as much as, you know, I'm sure you all hate hearing me say that over and over again, day after day, but it's important because, you know, it's a good sign here that I've wound up with a result that is dimensionless, right? Because cotangent of 75.5 degrees is just a pure number, and beta is a pure number, right? So I know that this is just some number. Now, I think that we just have to say that beta is equal to 1. Because that is when the contribution to the torque is largest, right? You don't have to do it this way. You could have just said also that this term here is just mg L cosine theta, right? And so that's okay too if you could see that, but like I needed to think about it for a little while at least to make sure that that sort of made sense to me. So let's just take the limiting case then, where I'm going to make Mathematica plug the numbers in because, you know, I think people like numbers. I mean, I don't, but I think you guys do, so. Despite however much I tell you, you shouldn't. Okay, so I'm getting that this is approximately equal to 0. Let's keep 3 decimal places. Why not for now? So 0.216, right? And I mean, that's a reasonable value, right? Typically the static friction coefficients are between 0 and 1. But let me just come back to the problem statement real quick and make sure that what I'm saying here makes sense. So we set the torque exerted on the ladder by the person to be the maximum value it could be, right? And that corresponds to when the person is the farthest from the axis of rotation. Okay. And he says, what minimum static friction coefficient between the ladder and ground did the manufacturer plan for? So I would say that it's reasonable to think that the minimum static friction coefficient corresponds to the maximum torque that the person must exert on the ladder, okay? So I want to say that this is our answer without really any further, you know, analysis of it, right? But these static friction problems can be tricky because, again, right, static friction is defined via an inequality, unlike kinetic friction, right? I think this is good though. Okay, so yeah, I would suggest that, you know, kind of you try to work through this yourself and think about the fact that static friction is defined via an inequality and make sure that this makes sense to you. But I think this is a good result. Okay, so hopefully this helped. Obviously, if you guys have any questions, you know, feel free to reach out however you want to. You know, I don't expect or really even want you to follow me on YouTube, but if you want to follow me on Twitch, I'd appreciate that. Okay, all right, I'll see you guys later.